In 1826, George Simon Ohm, a German physicist, carried out experiments with different metal wires. While he was carrying out these experiments with different metal wires, he discovered something that will be the basis for our discussion in this video. In each of these wires, he was measuring the potential difference across each of those wires, and he was also measuring the current that was going through these wires. And in his investigations, he came to this conclusion that the ratio of the potential difference between the ends of the conductors, or the ends of these wires, to the current flowing through each of these wires was constant. Now, this relationship between the potential difference across the wires and the current going through each of these wires is what we call Ohm's law. Now, in this video, we are going to look into Ohm's law experimentally and see how we can also arrive at this relationship. Now, right before us, we are having a circuit diagram. In this circuit diagram, we are having a dry cell. It is just one dry cell. It is connected to an ammeter and then rheostat. Then the rheostat is connected to a certain wire. This red thing you're seeing is just a representation of the wire. In my experiment, I will use a Constantine wire. The terminals of this Constantine wire are connected across a voltmeter, and this voltmeter is definitely going to be measuring the potential difference across this Constantine wire, and then this continues to a switch. This is how we are going to connect our circuit following this circuit diagram. Of course, if you look at this cell, this long end is the positive terminal, this short one is the negative terminal. So we are going to connect the negative terminal to the ammeter at this point. So looking at us, I had already connected the circuit. If you look at this is our ammeter right there. Because of that A, it's our ammeter. And of course our ammeter, we are connecting, this is the dry cell we're talking about. This is the negative terminal of the battery, and that's the positive terminal. So we are going to connect the negative terminal of the battery to the negative terminal of the ammeter. And of course, it is always black. The red ones are where the positive ones are connected. So we connect the negative to there, and then this is where the circuit continues to the rheostat. This is our rheostat right here. We are connecting one of the wires right here. Current is going to go through here and go through one of those coiled wires, and it will get out from here via this wire, the electrons flowing from negative. So this is our rheostat, and it's having a maximum of up to 20 ohms. So our rheostat is right there. So we connect the terminal that is leading out of the rheostat, we connect it to our wire. Now our wire right here is from our rheostat. We connected this to our Constantine wire. We have held our Constantine wire onto a ruler right here. So we fastened it onto a ruler. And so our Constantine wire is held right there, up to there. And of course, if you look at our circuit diagram, this continues up to the switch. And this right here is our switch. This is, so if we are to complete the circuit or to close the switch, we simply get this and close it there, and the switch starts working. But for now, it is still open. And definitely, of course, the other terminal of the switch is going to lead to the dry cell, just like the circuit diagram says. So this is our circuit diagram. And so now, of course, we are going to now connect this voltmeter across this. Now the issue here is we want to investigate Ohm's law. Now this is the conductor we shall be using to investigate Ohm's law, or to verify it. Now this conductor will be having current going through it. Now this current that is going to run through this conductor will be regulated by this rheostat. So it means that as we regulate this rheostat, we will be regulating how much current goes through this rheostat. Then this voltmeter is responsible for measuring the potential difference across the ends of this wire, this Constantine wire. So in our connections, we are supposed to be very careful that the voltmeter is supposed to be connected correctly. This is the negative terminal of the battery. So it means that you're supposed to connect the negative terminal of the battery to the voltmeter correctly. And this other part, the positive terminal of the battery, is supposed to be connected to the voltmeter correctly. just like the way we did with the ammeter. Regarding how to correctly connect a voltmeter and an ammeter into a circuit, I explained that in detail in the previous video. According to our circuit diagram, this is the negative part from the cell, the negative part of the cell right here. So it means that we're supposed to connect this negative to the voltmeter correctly. So it means that if you look at our voltmeter, the negative portion is here. So if you're to follow our circuit here, this is our rheostat. The wire gets out of here, gets to this point. So this terminal here, this wire, is supposed to be connected to the negative part right there. And again, to determine where whether to place the positive here or the positive there, I explained that in the previous video in detail on how we choose which terminal to connect here. The same with the current. On on how to choose this or that, I explained that previously in our video. So we continue with our experiment. So this is connected to the other terminal of the wire, which is right here. These are crocodile clips, are the ones we are using to connect to the ends of this wire, the Constantine wire. So definitely, and this connects to the switch. So after connecting our circuit like that, it only requires us to close the switch, and when we close the switch, we're able to get the voltmeter reading and the ammeter reading from our circuit here. So now that we've set up the apparatus, how do we conduct this experiment? So first of all, we are going to close this. We close the switch. After closing the switch, it means that our current is moving through the circuit. And if you could look here, our ammeter has deflected a bit. I don't know if you can see it. The voltmeter is already deflected also, and the current. Now, of course, this is our rheostat. We shall adjust our rheostat. We can adjust our rheostat anyhow to vary the resistance. Now we adjust it in such a way that our resistance is very big and the current is reading small. So we want to start from a very small current and then we keep on increasing. Now I'll just demonstrate how we do the experiment. So what we do here is, number one, we are going to adjust the rheostat here to start with a large value of resistance. That means if it's the large value of resistance, it will be reflected by a very small amount of current. So when we start with the large value of resistance, next is we read and record the ammeter reading and the voltmeter reading. Now for example here, our current here is reading 0.1 amperes right here. So 0.1 amperes, and our voltage, the corresponding voltage across the wire, is reading 0.2 volts. 0.1 here it's reading 0.2 volts, our voltage. So while after we read that very fast, then we open our switch, we record the ammeter reading and the voltmeter reading. The ammeter reading and voltmeter reading are recorded in a table like this. In this column, when we measure the ammeter reading, we write the ammeter reading here in amperes and then the voltmeter reading right there. Then after that, we continue with our experiment and adjust the rheostat to get other values. So in simple terms, we are going to adjust this rheostat. When we adjust this rheostat, we close the switch and we are able to get new values of current. So we shall repeat this experiment like that by changing the rheostat. As we keep changing the rheostat, we keep getting new values of A and V. Every time you change the rheostat, you measure the new value of current and the new value of voltage. You can do it like 5-6 times so that you're able to get values of current and values of potential difference. As you get the values of current and potential difference and you plot them in a table like this, then you will go ahead and you draw a graph. You will draw a graph of potential difference V against I. And when you plot the graph of potential difference V against I, you will come up with a straight line. Now we were adjusting this rheostat for us to be able to get new values of current, so that as we get new values of current, we are able to get new values of voltage. We're using rheostat. Now sometimes you can just leave the rheostat intact, and instead you use another method of varying the amount of current so that you get new values of voltage. How can you do this? We connect the apparatus just like the way it is. Then we shall adjust this rheostat with our switch on. We adjust the rheostat in such a way that it measures a very small amount of current. In this case, it is measuring around 0.1 amperes, as you can see. I hope parallax is not disturbing. It measures 0.1 amperes. So when it measures 0.1 amperes, the voltmeter is also deflecting. So you close the switch and you measure your value of V and A, and you record. After recording, you disconnect. Here we're using one battery. So afterwards, after getting, you open the switch and then you disconnect this and connect now two dry cells on top of this. This was one dry cell, now use two dry cells. When the rest of the circuit is still the way it is, you connect the two dry cells now. You get two dry cells, connect the positive and the negative. After connecting your two dry cells into the circuit, close the switch. After closing the switch, measure off your ammeter reading and voltmeter reading immediately. Afterwards, you open your switch. You add now the third unit. You use 3 dry cells, and again after do 3 dry cells. When it's now 3 dry cells in the circuit, measure the ammeter reading and the voltmeter reading. Afterwards, put the 4th dry cell in series. After putting 4 dry cells in series in this circuit, measure the ammeter reading, measure the voltmeter reading. Then after you've accumulated up to 4 dry cells, you've put your table of results. You've put your results in a table like this. You've been able to measure the current and the potential difference. After measuring the current and the potential difference, you draw a graph of potential difference against current. When you plot your graph of voltage against current, you will realize that current is directly proportional to voltage. By saying that current is directly proportional to voltage, I simply mean that every time the amount of current increases, voltage also increases. When current increases to this level, voltage also increases to that level. When current increases to that amount, voltage also increases to that amount. So from our experiment, we are able to see that voltage is directly proportional to current. Now, if voltage is directly proportional to current, this means that the slope of this graph is going to give us a constant figure, or it means that when we get the amount of voltage at each of these points and divide it with the amount of current, we are going to get a constant figure, or call it a constant. And this constant is what we are calling resistance of this circuit. So this brings us to Ohm's law. So from Ohm's law, he simply stated and concluded after that experiment that the current through a metallic conductor is always directly proportional to the voltage or to the potential difference across the ends, provided temperature and other physical conditions are held constant. Now, if you look at this table of results from an experiment carried out earlier, you'll find that for every amount, these are the amount, the current, and this is the potential difference. When we divide V by I, we get a constant, and this constant is what we are calling resistance. And this resistance is measured in ohms. It was named after the guy who found this out. And looking at Ohm's law, emphasis is placed on the metal conductor, and this is because other materials behave differently. Materials like nichrome wire are not so much affected by temperature conditions, and so in most cases nichrome wire is always used in these kinds of experiments. I used Constantine wire, and well, Constantine is also not that bad either. It gets the work done. So looking at this law, we are able to see that voltage, they are telling us that current is directly proportional to voltage. So it means that V is directly proportional to I, or current flowing through a conductor is directly proportional to the potential difference across the ends of that conductor. But now if we are to remove that proportionality sign, it means we're supposed to introduce a constant of proportionality, and it means that this is going to become V is going to be equal to K times I. That is, if to remove this proportionality sign, we introduce a constant of proportionality, and that constant of proportionality so happens to be the resistance of that conductor. So it means that V is equal to R times I, and if we are to make this R the subject of the formula, we know that resistance is going to be equal to V over I. Just like in our table of results, we're able to show that R is equal to V over I. It's constant all through from all the values that we got in our experiment. Now this constant of proportionality R is called the resistance, and this resistance is in ohms. It was named ohms after the inventor himself, George Simon Ohm. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.